People should be logging on. No. Oh.
Hello, everyone. We have Warren Hornsey here, who will be presenting today on geosynthetic interface friction avoiding failures. This is our webinar number 46 of A6, so Australian chapter of IGS. My name is Alicia Borysewicz-Słabik. Hello, Warren.
Hi, Alicia.
I am going to share my screen. Okay. So before we start with webinar, I will have some words about our organization. So IGS is International Geosynthetic Society, which has 45 chapters globally, representing 50 countries, 4,000 members, including corporate, individual, and student. We have some upcoming events that I wanted to share with you for the next year. So we have Educate the Educators, which will be at the end of November. Then we need some sponsors for that. So if you are interested, please just contact us. We have also a workshop/roadshow, which will be in 3 Australian main cities and New Zealand. We plan it for about August 26. And also in mid-2027, we plan GeoANZ number 3, and it will be in Perth. More details will be coming. We are still in the very early organization stage. Also, we have some webinars coming, which at the beginning of the year. Today's is Warren's that will be finishing our 2025 webinars, and we have our IGS handbook overview webinar with Samalant and Heidi Abdiel, which will be early February. We are selling IGS handbooks through our chapter, so it might be handy for you to have a look what's going on and get some details. Also, we have other webinars in late February and March, which will come up with advertisement in the new year. All of these are thanks to our sponsors and company members. So thank you for all of them for our support. Without you, we couldn't do anything. And if you are not yet the company member, we would encourage you to sign up. There are multiple benefits. So if you are interested, please contact us. So about Warren. Warren is director of TRI Australasia. Everyone knows him here in Australia, probably don't need to introduce. Warren is professional civil engineer and has worked in the civil engineering field in Africa, Europe, and Australia. He has been active in the geosynthetic field since 1997, with experience in geosynthetic testing, research and development and design of structures involving geosynthetics. His experience covers a diverse range of geosynthetic applications, from landfill lining to reinforcing and coastal protection. He has published over 20 peer-reviewed technical papers relating to geosynthetic design and applications. If you have any questions, please post in the Q&A, and I will read it out loud at the end of the session. If you need certificate of attendance, please contact us. Okay, off to you, Warren.
Thanks, Alicia. Okay, so today's presentation is on geosynthetic interface friction testing and avoiding failures. While I'd hoped to have spoken a little bit more on avoiding all failures, but by the time I'd finished most of the presentation, there wasn't much time to talk about the failures, so that may be another subject for a later date. So in terms of slope stability, it's probably the most largest challenge facing stakeholders these days, mainly because it's such a it's so in your face. When there's a failure, it can't be missed. And it normally costs many hundreds of thousands of dollars to remediate. These failures are not new. One of my first jobs that I went to when I was starting out in geosynthetics in 1997 was a landfill failure in South Africa. And essentially that failure destroyed the company who did the design. While in the long run, they were found not to have been liable for the failure. It was more the operator of the landfill that was at fault. By the time that came out in the court case, people had moved on to other companies using it for design and so on. So it's really it's a real problem for many engineers. In terms of this, in the Australian perspective, we've seen a dramatic increase in interface friction testing over the years. Back when we started in 2013, we had 1 shear box. We now have 5 shear boxes, and those pretty much run all year long, every day on various projects. But what we're seeing is that there's not a lot of understanding of what goes on in terms of the interface friction testing. And people don't really have a good feel of what the standards are. And we often see poor specifications or awareness in terms of how to set up these tests and how to perform the tests. So the idea of this presentation was to provide an overview of what this is about, and I'll be going through some of the standards and highlighting the key areas within those standards. And the idea is that you can use this presentation as a cheat sheet, really, to when you're going ahead and doing a design or specifying, that you can use this as a bit of a guidance tool along the way. So, talking about landfill failures, this is kind of the dramatic outcome that nobody really wants to see, is these slips either through the waste onto your cell, or in this case of different components within the liner system sliding down the slope. So like I said, this is nothing new, and I was actually out on a site on Tuesday having a look at a similar failure that occurred in the Brisbane area. So it continues despite us doing lots of testing. So what do we need for this sort of testing? Essentially, for geosynthetic testing, you need large shear boxes. So 300 by 300 millimeter shear boxes, not your 75 or 50 millimeter shear boxes that you use for soil testing and so on. These are specialized pieces of equipment that have special adaptations that are beyond what a normal soil testing apparatus would do. And because of the large area, we're talking about large loads, and those loads are applied either through hydraulic rams or applied by air pressure. So it really depends on what equipment you've got. And essentially what we're doing is that we're applying a normal load or a vertical load on the specimen, and then applying a horizontal shear stress. And from that, we can work out what the friction angle is and get an indication of the forces that are involved in or transferred through these materials as you fill up your landfill or build the landfill. So what we're going to go through today is the 3 key standards that are involved in interface friction testing with geosynthetics. ASTM D5321 which is really a guide on what you should be considering when you're doing interface friction testing. If you're a designer, you really should get this a copy of this standard and go through it, read it, and make sure you understand what it's all about. There's a lot of information in there, and while some of it is not may not be useful for you, there is a lot of information in there that can be really helpful. And I'll go through a few key aspects of that today. The next one is ASTM D5321, and that's for doing geosynthetics versus soils, or geosynthetics versus geosynthetics. And then ASTM D6243, which is essentially the same as 5321. However, it works mainly with, well, it is for GCL specific interfaces. So whenever there's a geosynthetic involved in interface friction, a GCL involved in the shear profile, then you should be using 6243. The standards themselves are very similar, as you'll see. It really is just some of the setup details that is different in 6243. So in terms of 7702, the standard means while it's not really a standard, it's just a guidance document. And it means so when we say standard, it means it's been approved, the ASTM process. It's a summary of information that was available at the time of publication. It's intended to assist designers, and it's not intended to replace educational experience. And these are all the disclaimers associated with the standard itself. One of the key areas that it references a few people within that standard: Thiel, Gilbert, Kuhn, and Stark, and there's some documents that I'm going to show, or correspondence that I have with those people later on when we go through a case study. So it goes through what the shear strength fundamentals are, evaluation of Moore-Coulomb envelopes, comparing shear results with historical data, and evaluating multi-interface test results. So all of these sort of things are covered in 7702. And like I said, it's a very useful standard, and I would recommend everybody that's getting involved in shear testing get a copy of that standard. The next one is ASTM 5321, which is this is the testing method. So this is going down to how you should test these materials. And I spoke about the 300 millimeter shear boxes. These are the requirements of the standard. And within that, they talk about shear displacement rates, displacement indicators showing that you need to have at least 75 mils of shear when you're testing it, how you clamp those materials in place to make sure that the materials are forced to shear along the interface that you want it to shear, not that it shears on the gripping plates along the way. And what I've shown you down the bottom here in the images is the pyramid gripping teeth, which is really good for GCL type testing, or where there's geocomposites where you really need a good gripping surface, to sandpaper surfaces, to this is the GRI version. It's like those gang nail gripping surfaces like you use on roof trusses and so on. And then over here is just the clamping devices for the geosynthetics themselves while they gripped underneath here is a secondary clamping to hold the samples in position. So the standard talks about them, but doesn't give you guidance on what you should be using. Again, in terms of conditioning, the standard talks about being aware of the conditioning of your samples. It talks about the time that it says you should consider the time those samples should condition, but it doesn't give you any guidance. It doesn't tell you to do it 1 hour, 24 hours, 48 hours. Those are engineer specific or site specific. The same with confining pressures and normal stresses and shear rates. It doesn't give you too much information on it because each one of those things is project specific, and design engineers really need to think about what they do, what they should be doing. So in terms of normal stresses, I see this quite often. We see capping designs with 200 kPa confining pressures being specified and things like that, which is really unrealistic for a capping design. So from a design engineer perspective, you really need to think what your loads are that you're going to be applying during construction and how that will affect your interface friction testing. So there's procedures that you would follow if you were doing geosynthetic versus geosynthetic, say a geocomposite against a geomembrane. They talk about how you'd assemble the layers and so on. Now, in terms of applying the shear speed or shear force, if there's no instructions, the standard says 5 millimeters per minute. Well, in all reality, I haven't seen any shear being carried out at 5 millimeters per minute here in Australia. Having said that, in the US, it seems to be the norm with, say, a geomembrane versus geocomposite or a geotextile versus a geomembrane, those sort of things. So that's where that becomes interesting. But in Australia, we don't see anything faster than 1 millimeter per minute. And I think the small gain you get from running at 5 millimeters per minute is negligible. The standard requires you to run to 75 millimeters. However, there's a note that allows you to stop the test once steady state is achieved, and I'll go into that again because it's quite important. I've gone into this in a bit of a detail at the end of the presentation in the case study. And then there's requirements of identifying failure mechanisms, photographs of failure surfaces and so on, and whether the failures happen within the specimen or at the clamps and so on. So it's quite detailed in terms of what is required or what should be reported. Now, much of these procedures are very similar, other than, say, soils, where you have to know what the compaction of your soil is and what the density and moisture content is going to be. And then there's some guidance in terms of what the excess pull, what speed you should run on. In terms of reporting, it's really detailed in terms of what should be reported and what you should be expecting when you see results come in from the shear testing. It really needs, description of the specimen. So if you're using grade X GCL, you need to describe what the grade of geotextile or GCL it is, because that grade could have an effect on the outcomes of your testing. So if you look at this graph over here, you can see this is a GCL against the geomembrane, and in this case, we're getting internal failure of the GCL. And this may not happen if you have a different grade GCL. So it's really important that these are standard requirements of what's required in the standard in terms of lots of shear force versus displacement, shear stress versus normal loads, standard sort of tests, but are not always provided to clients for them to assess. So in terms of what the laboratory should be supplying you is the friction angle that you would expect out of those materials, secant friction angle, so the angle is if you took the line through zero cohesion, and then the mode of failure. So you can see on these images down here, we've got a geocomposite against the geomembrane, and you can see the geocomposite is clearly slid against the geomembrane because there's nothing sticking out the back of it. In this case here, we look at a GCL that's failed internally, and the same with this one over here, where the GCL is basically sheared internally, and there's no bond between the upper and lower surface of the GCL. So those are the sort of things that you should be getting. You don't always get this from a lab unless you ask for photographs, but the lab should be taking photographs of all their interfaces. So next one is 6243. Again, same sort of, or same setup. It's the same. We use exactly the same machines. But in here, we're talking about displacement rates of between 6.35 millimeters per minute down to 0.025 millimeter per minute shears. And that really has to do with whether the excess water, poor water pressure is building up in the specimens during the shearing. And the keys, again, are preventing tensile failure of the geosynthetic outside of the confinement area. So we confine it within a 300 by 300 millimeter area, and that's where you want the failure to happen. You don't want the geomembrane going into tension around the clamps on the outside of the sample. Again, it's much the same as the 5321, that it's the same setting up in terms of conditioning, although once again there's no guidance, just saying you have to consider this, and you have to define what that requirement is for your testing facility. This standard again goes a little bit more detail in terms of the shear, applying the shear force. They're talking about 1 millimeter per minute for interface shear strength and 0.01 for internal shear strength. Now, I don't really agree with that, to be honest. If you're going at 0.1 millimeter per minute for internal shear, you should be applying the same thought process for the interface friction testing. I think you'd struggle to justify running a GCL against another interface, say a geomembrane, where you can't release poor water pressures at 1 millimeter per minute when you're testing. But again, showing the failure mechanisms and so on along the way. They talk about the different interfaces, so the procedures in terms of setting up the GCL versus geosynthetics and so on. So there's a little bit of detail in terms of how that should be set up. And this is something that you should be transferring over to your laboratory that's doing the test. And there's details. So if you're doing GCLs versus soil, and you place the GCL in the bottom box, that's okay if your GCL is not prehydrated. But the moment you prehydrate your GCL, and we see this regularly, the GCL becomes very plastic, or the clay within the GCL becomes very plastic, and it almost turns into a toothpaste where you can just squeeze it between your fingers. So if you compact on that, you could be squeezing all the clay out of the GCL, and then you're not testing the true performance of the GCL. So you have to be careful of that. So while the standard gives guidance, think about what you're doing in terms of the way it's going to be set up and so on. The reporting is exactly the same as 5321. So there's no difference. They're really asking for the same processes. So I haven't added more photos into these things because it really is the same. What the standard does have in it is a checklist in terms of what you should be supplying to your laboratory for the testing purposes. And so I would say, again, that you should get a copy of each of those standards. And when you set up your test requests, that at least you confirm that you ticking off these this checklist in terms of what needs to be done for the testing. So your specification is your specification covering all these items that are listed in the test in the standard. So the specification is the design engineer's responsibility, and really the setup of the test program should be the designer's responsibility. Don't leave it up to the CQA person on site to make that call. While it might be him that has to, or them that needs to see if it passes or fails, they should not be the ones deciding how those materials are set up in the test. And you really you need a justification if you deviate from the standard, particularly if things go wrong. When things go wrong and material starts sliding down the hill. If you deviated from what the standard says, you need to have some sort of justification as to why that would be. Because from my experience, when lawyers get a hold of something and get involved in projects like this, it doesn't matter whether it's right or wrong. It's whether you followed the standard or not. And if you haven't justified why you deviated from the standard, then it becomes you've almost assumed responsibility or certainly co-responsibility for any sort of failure that is out there. So in terms of the specification and testing, number one, make sure the laboratory is testing the correct material. It's no good asking the laboratory if they've got some clays that they think will suit your site. That's extremely dangerous. I mean, clays are so variable, and we see big differences in terms of plasticity index and particle size distribution of some of these clays. Some of them have sandy materials in them. The materials out of WA have a lot of sand in them, whereas some of the sites that we see around Melbourne and so on are highly plastic, very fine, very slippery clays. So substituting clays is extremely dangerous. Geomembranes, we all like to think all geomembranes are the same, but there is a difference between blown film and flat die textured geomembranes. And the next slide will show the type and size of texturing, whether it's a glossy surface or a dull, smooth surface. And I've got some examples of what we see here. So this is a smooth geomembrane. One of them has a very shiny surface, whereas the other one has almost a matte finish on it. Then we go to a single-sided textured. One will have a slightly uneven surface, and the other one's, so this is a blown film, the smooth side of a blown film geomembrane, and this is the smooth side of a flat die geomembrane. So they are slightly different. So again, swapping materials is not ideal. When we talk about textured geomembranes, it gets even more complex because we have blown film and there's spray textured, which I haven't got a photograph of, and then flat die texturing and these little indent or the little bumps on the geomembrane changing shape and size and spacing and so on. So all of those characteristics will have an influence on your shear results. So if you plan on using a certain material, don't substitute for somebody else's material because it's easy to get hold of. In terms of GCLs, clay impregnation of the geotextile, the upper geotextile or the geotextile that's facing whatever you're shearing can have an impact on it. In this image over here, you can see extrusion of clay onto the surface of the geomembrane that we're going to shear against, and that can have an influence on the shear values. Heat setting of the GCL. Is it heat set? How well is it heat set? Peel strengths of the GCLs. It absolutely makes a difference to the peak strength or peak shear values that you will get under high confining pressures. Not so important under low confining pressures, but certainly under high confining pressures. The peel strength of that GCL will have an influence on the friction angles that you get out of the system. And then any coatings that you may or may not have on that GCL. We did a job a few years ago in Papua New Guinea where a plastic coating was placed on the attached to the GCL. And it was probably a bit of a slip of the tongue, but in my opinion, it was placed on the GCL rather than attached to the GCL. So the failure plane became the coating or the attachment of the coating to the GCL. So be aware of those sort of things. In terms of geotextiles, there is a difference between continuous filament and staple fiber geotextiles in terms of the way they react to the shear, in terms of the speed at which they take up the forces. And then needling density. Needling density for non-woven geotextiles, if you have a fluffy geotextiles, we can sometimes get internal shearing of the geotextile as we're shearing it, depending on how well it's needled together. So lightly needled materials can shear internally when we test them against a textured geomembrane. And geocomposites, ply adhesion is really important. I mean, this is an indication of a sample that came out of the shear box, and there's bonding on these edges. Down the middle, there's no bonding. That's going to have an influence. There's also the shape of the net itself, whether it's a sharp edge along your strands and the angle at which that strand, the force goes over those strands, has an influence. So all of this is important. So in terms of setting up the boxes themselves, I've set up some generic diagrams of what you should be doing. But because what we're measuring is a shear stress, so in other words, a force over an area, when you set up multi-component geosynthetics, you should always peel the material back so that only the area that is under the confining pressure is bonded. Because if you continue with this area that goes up in the clamped areas to leaving that bonded, that tensile strength within that area can influence the shear results that you can get and overstate your shear values because you're putting tension into the whole structure and so on. So we'd always recommend that only the area under the confining pressure is bonded. The same goes when we're going GCL or geocomposite against a geomembrane, that we would peel back the composite section so that only the section that's under confinement is bonded and the rest is free to shear. The geomembrane is clamped at the back, and the GCL, the top geotextile of the GCL, is clamped in the front. You can see the clamp there. It's that clamp sitting through there to hold the sample in position. So these are the sort of things that you have to think about when you're doing your test requests that you send through to the laboratories, because they can have an influence on the outcomes. One of the key areas that I see in this, we're seeing more and more geogrids being included into particularly veneer stability, landfill cap designs. And often we see there is no clamping of the geogrid in the layer work. So the geogrid is free to slide along with the material. The problem with that is that you are not really measuring that shear force. You're not measuring the real forces that are going into your geogrid, and you could be underestimating your forces going into your geogrid. And why that's a problem is that you can underestimate your forces going into your geogrid, underestimate the anchorage required for your geogrid, and you could have pull-out failure of your geogrid, and you have the whole structure slide down the slope because of that. So think carefully when you're doing these geogrid inclusions in there in terms of what is happening on site and how that interaction is going to happen. It's no good having a geogrid floating in the shear box if it's not floating on site. If it's anchored in a trench and it's designed to be a reinforcement, it should be anchored in the shear box to replicate the same thing happening there. So, in terms of testing, you've got to think about what the hydration requirements are that you're having, and these are typical hydration periods that we see. I'd say that's probably not 96 hours. It's not typical, but we have done testing, hydration or consolidation for 96 hours. Step loading, we see in some applications, but you need to be aware that this adds time to the testing. And then once you've done step loading, do you shear immediately afterwards, after you've reached the 500, say, kPa, or do you hold it for a period of time? 16 hours, 24 hours, whatever it is. And then in terms of your shear rates, what are you specifying and how quickly can these tests be turned around? So 1 millimeter per minute, 75 minutes, less than an hour, just over an hour for a test. 0.1 millimeter per minute, that's 12 hours of shearing. 0.02 millimeters per minute, you're talking about 2.5 days of shearing to get that. So just be aware of that. And this is an example of a project that I'm coaching right now. And you can see that we've got 3 confining pressures. We have to have 48 hours of hydration, step loading at 12.5 kPa an hour and 0.1 millimeter per minute. And we have to do that 3 times. So essentially, we will have 1 shear box tied up for almost 3 months doing something like this. So that's fine. We can do it. But your results are, there's no way of speeding these tests up. Then you're waiting 3 months for results. In terms of understanding the results, what you should be getting as per the standards are what the specimen is, what the normal load is, or normal stress that you've applied to the specimen, so 150, 100 to 350 kPa, the shear stress, the peak shear stress that was recorded, so those values there, the large displacement shear stresses that are recorded are those ones, and then we're looking at the friction angle, and for both peak friction angle and the large displacement friction angle. So that's what you should be seeing in a report, at the very least. It's important that you as design engineers or CQAs understand that all these materials have a fingerprint, for want of a better word, in terms of how they would behave, depending on what materials are being sheared, whether it's smooth geomembrane against geotextile or textured geomembrane against GCL and so on. One thing's really important to understand is that all of these materials need some movement between them in order to take up that force. It's not an instantaneous force transfer. Smooth geotextile is probably the only thing that's instantaneous because the forces are so low and there's no gripping or interlock required between anything. But as soon as you use textured geomembranes, it takes a while for those materials that are in contact with the textured geomembrane to lock into that texturing and then take up some sort of tensile force within that application. So when you're getting results, have a look at them and say, does that look reasonable for a textured geomembrane against a GCL or whatever the case may be? We can certainly give you some guidance on that. And there are some examples that can be shown for those sort of materials. Things like internal shearing of GCLs or its geosynthetics. GCLs, if they're fully hydrated, will normally fail at confining internally if there's confining pressures of greater than 150 kPa. It depends on the grades, but what you can see here is that this low confining pressure of 100 kPa, what's happened is the GCL is sheared against the textured geomembrane, and we're getting the large displacement shear stress being reasonably high. We've gone to 300 kPa, we get a peak, but at this peak, what's happening is that the GCL has failed internally. And therefore, at the end of the day, when we go down to the large displacement, it's much lower than what we're seeing at 300 kPa. The same is going for 500 kPa. And if we continue these shear stresses out to 300 millimeters, these numbers here would converge, and you get essentially the friction angle of a sodium clay, which is anywhere between 3 and 4 degrees. So very small. In the case here where we have this, the shear stress at higher confining pressures being less, what we get is a negative slope, which can't be, that's not real, because that's just a theoretical number. We would force the tangent through the zero so that you've got a more realistic friction angle or large displacement friction angle, something like that. But again, your laboratory should be telling you that that's what they've done when they've done the testing. And you should be checking that if that's occurring along the way. So, as a final test, and I'm running a bit over time already, there's a quick case study that I'll go through. So there's 2 laboratories carried out testing on the textured geomembrane versus the GCL. Laboratory 1 used a different grade of GCL in terms of, so grade X was specified. They used grade Y as their GCL for the testing. Laboratory 2 used the GCL specified, and it was set up as per slide 28. So you can go back and have a look at that slide. And what you see here is the differences in the shear stress. So stress versus displacement. With laboratory 1, we're getting at 600 kPa, we're getting just over 160 kPa shear stress. Whereas laboratory 2, we're getting up in the 270 kPa shear stress for the same, supposedly the same interfaces. So that set off alarm bells with the design engineer, and so hence the comparison that was carried out. And what you can see is that the lab 1 stress displacement looks a lot like a smooth geomembrane versus geotextile. Not quite there, but it's pretty close. The displacement was only 18 millimeters, and there was no internal failure above 150 kPa. So there's some questions over how the material was clamped and so on. And what you can see in terms of the differences is that the shear stresses for each of the confining pressures, and you can see up to 93% difference. It's a huge difference in the results. And in friction angle, around 60% difference in friction angle. So we can drill into that even more and look at why that was stopped at 18 millimeters. And I highlighted this in the previous presentation, is that this test may be stopped sooner if the shear forces have reached steady state. And that's in both standards. And there's no definition in terms of the standard and what is classified as steady state. So what I did was I went and spoke to the experts that are listed in 77702, to George Kerner, Rick Teal, and Tim Stark, with a number of questions regarding this 75 mils large displacement shear stresses. And basically asking whether 75 millimeters is reasonable. And while both George Kerner and Rick Teal said that there was that's what's essentially industry practice, and that's what is used, that's acceptable. Tim Stark, on the other hand, said absolutely not. You should be using ring shears, and you can get much lower residual strengths, around 45% of the 25 to 75 mil displacement. So, and then the next question was, what is this end criteria if you're wanting to stop at shear testing early? And both George Kerner and Rick Teal gave insights on how they would see it. Again, it's very much up to the end user at the time to make a call on where they would land up in terms of accepting or not accepting that difference. And the third question was really, if you were running a test, would you leave it up to the laboratory to decide when they stop that test? And basically George Kerner saying, no ways would he ever stop a test early. There's no value in for the small amount of cost savings that you get. There's no engineering value in stopping it sooner. And then Rick Teal was saying that normally the project should require 75 millimeters, and that's what's readily available. But he can't find he can't find a reason to stop it before 75 millimeters, and that if there was a lawsuit, then it would come down to experts deciding on which is the right way to go. So nobody's really willing to give their full opinion on that side of it. But what I did was then go and have a look at a number of cases where I looked at whether terminating early, what difference that made to residual or large displacement shear stresses. And you can see that the shorter you make the sooner you stop the shear test, the greater the difference is between the shear values that so this is 50 millimeters displacement versus 75 millimeters, 26% difference. 60 millimeters versus 75 millimeters, say 10% difference. So it does have an influence, and really, as an engineer, you have to make the call whether you're going to accept those lower shear values along the way. So to finish off the test, and I've run a bit over time, shear testing is about as close to a performance test as we get in Geosynthetic. So it's really important that you set up the test as close to what you think is going to happen in the field as possible, because it does have the setup has an impact on the test results. These are not quick tests, and some of the tests will take months. And I understand people want to do replicate tests and so on, but be aware that those are time-consuming tests, and you are going to wait for those results to come out. Designers and specifiers need to understand what they're asking for. So again, go back, read the standards, make sure you're familiar with what the laboratory is testing and what you want out of those results, and make sure the lab understands that before they do the testing so that they can give you the right answers. And then lastly, with all of this testing that we do, laboratories make mistakes. So don't be afraid to ask for clarification if things don't look right. Or if you see something that looks unusual and you don't understand why a stress curve looks unusual. You as designer engineers and end users have every right to go and ask the laboratory for clarification on this. This is something that I would recommend that you do. If you see something that looks unusual, go back and ask the lab to clarify. And labs make mistakes. So it could be that they've set something up wrong and have to go back and rerun tests. So that's the end of my presentation. Hopefully I haven't bored everybody to death.
Thank you, Warren. That was very insightful. We have a few questions. Can you open Q&A so that you can see them? We have a few minutes so we can read them. Thanks. That's from Jonathan Shamrock. Thanks, Warren. Any comment on standard shear boxes versus ring shear type equipment and the impact of the limited strain in a standard shear boxes for interpreting post-peak to true residual interface shear strength?
Yes, so look, there's no doubt about it that the ring shear equipment does give lower residual shear strengths from those materials. That paper that I've referenced in the presentation gives some guidance on how to estimate what it would be if you ran with a 300 by 300 shear box in terms of what those residual numbers are. I mean, there's, like everything, there is advantages and disadvantages of the different methods. The ring shear specimens really use much smaller specimens, so edge effects become more important. So there's advantages and disadvantages with both methods, but yes, that paper that I've referenced by Tim Stark gives some guidance on it. Okay. Hopefully that answers the question.
And next one is from Jabolili. Hi, Warren, do you, as standard practice in your lab, discuss the design with the engineer prior to testing? Think it would add value making it a compulsory section of the test request that a brief discussion of the design or sketch of the barrier system be approved?
Yes, okay. So, yes, that's part of, okay. If we get in a shear request that we think is unusual, we will query with the design engineer if they really want that to go. So if that's really what they want, or if there's been some miscommunication. But that's no guarantee that every laboratory is going to do that. And in all honesty, sometimes it might come through and my guys don't necessarily pick it up. My technicians do it on a regular basis, so they know what they're used to seeing, and if they don't, and if it's close, they may not come back to anybody. So yes, I would say that it would, as a laboratory, we would certainly appreciate somebody showing me a diagram of exactly how the samples should be set up. We do have some standard diagrams which we give to customers if they need sort of clarification on how we would set it up.
Another one is from some anonymous. For GCL needling density, other than peel strength testing, are there any other standard testing done to get information on this?
Not to my knowledge. I don't know. And look, that certainly does have an impact. Needling density, and then also the volume of fibers, or the amount of fibers that are being transferred through the GCL during the needling process can have an impact on peel strength. I'm not sure how you would specify a needling density and then test to see whether that. So it's one thing specifying a needling density. It's another one testing to verify that that's the needling density that's been achieved. That would be the problem with needling density, I would say.
Okay, thank you. And so asked, how does different types of gripping, clamping system affects the result in different confining pressure? Do they have an influence?
Yes, absolutely. So particularly, the clearest way to see this is with, say, GCL internal shears. So if we're gripping a GCL and we try to do the internal shear strength of it, if we try to grip it with, say, a sandpaper gripping surface, it would basically slide across that sandpaper surface. And what we'd be measuring is the friction angle between the sandpaper and the GCL rather than the internal shear strength. And then at the friction angle between sandpaper and the GCL and the strength of portion of geotextile that's clamped on either end. You're going to measure the strength, the tensile strength of the GCL. So yes, if you don't have a good gripping plate, you are often measuring the tensile strength of the material that you're using, because then the force gets transferred through to the end clamps. Or if you don't have end clamps, then you're measuring the grip between your gripping plate and whatever is behind your gripping surface. So yes, it does have an influence. And I think the GCL4 paper, there's a specification, has some discussion on different gripping plates and so on in terms of how they perform against each other.
Thank you. And the last one, that probably will finish just on time, right? Case study, laboratory accreditation. This should remove some of these large discrepancies in testing between labs, right?
Yeah, yes and no. So the issue with laboratory accreditations, and I can be a little bit opinionated on this. So in Australia, we have NATA. NATA is very strong on, is your machine calibrated? Is your load cell correct? Do you have paperwork that says, my guys are trained, they've read the standard, they know how to do the test? They do very little in terms of inter-laboratory verifications. It's very much up to the laboratory to do that. And in most cases, particularly in terms of interface friction testing, from my experience, what I've seen people do is they test smooth geomembrane against geotextile. The easiest test that you could possibly do in terms of a shear test, because it puts very little load on, it generates very little shear stress and puts very little load on your gripping plates or your clamping devices. So yes, in theory, it should work, but in reality, it doesn't. So to give you an idea where NATA and GAI lab accredited, the GAI accreditation carries out testing with a smooth geomembrane against a non-woven geotextile at relatively low confining pressures. So very easy to compare results. Not a great way to test whether your gripping plates and your clamping for other products works very well. So again, it's one of those yes and no answers. Yes, it should. The actual inter-laboratory testing sometimes leaves a little bit to be desired.
Thank you. Thank you so much. And I think that's it with the questions. If anyone has any question, please send us an email on info@a6.org, and then we will just send it to Warren to respond. Thank you, Warren. That was very interesting. And yeah, as a installer that I'm usually dealing with you between you and the contractors, I always try to explain them that, look, this is 3 months test before even you order the materials, and sometimes they can't understand it. So it's always a grief from our end. Thank you for explaining that.
No problem. And if anybody wants the Stark paper that talks about the transfer from to the ring shear testing of large displacement, just send me an email and I'll send you the paper.
No worries. Thank you. Thank you everyone for joining us. And we will post the recording of that session soon on our website. Thank you. Bye.